Okay, well, thanks, David. I'll introduce you and then we could start. So thanks everybody for coming. David Kault, believe it or not, Sam Kault's father. So I'll make that connection. Most of us know Sam Kault from the School of Mathematics and Physics, and David Kault, his dad is presenting up from Townsville. So thanks for joining us from there. So David is a GP and also a mathematician. And as far as I understood, David moved between these two roles over the years, both working as a GP and a mathematician. In the last couple of years, David's been working as a GP also with First Nations people and with all kinds of things like that. One more interesting piece of information. I hope you don't mind I say this, David, that's I learned about you on Friday. You were jailed back in the day for a few days for protesting.
That's correct.
That's before the days of Facebook when people actually protested. But that didn't stop you from working as a GP in state penitentiaries recently. And we'll hear about branching processes and such. And are you okay with interruptions and questions as we go?
Certainly, anytime.
Okay. All right, go for it. Enjoy. Thank you.
Okay, so China has managed to eliminate COVID, and New Zealand has a policy to go for elimination, and Australia seems to be inarticulately drifting in that direction. So I thought it'd be interesting to consider the end stage of a policy of elimination. Some people are very negative about the possibility of elimination because they're thinking there's asymptomatic cases around. There's always a risk of the epidemic re-emerging, and of course it would re-emerge if we opened our borders to international travellers from places where it was still circulating. But I thought it was probably wrong to be pessimistic about the prospects of elimination. So my model looks at the last stage of a successful program to push down the numbers of symptomatic COVID cases until there's just one symptomatic person known about. And then restrictions within the borders are suddenly lifted and we go back to conditions where that single case could propagate. And the tool that I'm using is branching processes. And in the language of branching processes, the first person at the base of the trunk of the branching process is called the 0th generation, and then the next person is the 1st generation, and then there's the 2nd generation. Slightly different if we're talking epidemiology, we'd call the first person the primary case, and then the second person the secondary case, and then you have tertiary cases and so on. But that's the idea, and of course this is all stochastic. So nothing happens except definitely it's all probabilistic. And so we could have extinction simply because the primary case maybe there's secondary cases, but all of them don't give rise to tertiary cases, or some of the secondary cases do, but some of the tertiary cases don't. So there's all sorts of permutations and combinations, and it looks like it's an impossible task to find out the overall probability of extinction, but I'm going to show as a preliminary to my paper how this can be done. And first we start with defining our terms. So the number of secondary cases generated by a primary case, the chance of it being K secondary cases we'll call PK, P subscript K, and we're assuming that same measure is true for any secondary case or any tertiary case. It's all got the same set of probabilities PK. And the way we proceed is by wrapping up the information in this set of PK, P subscript K, into an algebraic expression, which we call a probability generating function. And we'll go on and look at the properties of this probability generating function, phi subscript x of z. And first of all, we'll substitute naught for z, and we see that that's p naught, and that's a probability there'll be no cases, secondary cases generated by that person. And we assume this is going to be greater than naught, because otherwise extinction would not be possible. If we substitute 1 in for z, what we get is the sum of all the probabilities of 0, 1, 2, 3, and so on offspring, so that's 1. Now, if we take the derivative with respect to z of the probability generating function, we get P1 plus 2P2, we get P1 plus P2 times 2Z plus P3 times 3Z squared, etc. And this is positive. It's obviously a parabola, or steeper than a parabola. It's a convex function. And then if we substitute a 1 for the Z, what we get is P1 plus 2P2 plus 3P3. So it's 1 with probability 1, 2 with probability 2, P2, 3 with probability P3. So that's a probability weighted average of the number of offspring. That's denoted the expected value of X, it's the expected value of the number of offspring. And if we're using that expected value notation, it actually makes things easier. I won't use it that much, but basically this probability generating function we've defined could be thought of as the expected value of Z raised to the power of the random variable. It's Z to the 0 with probability P0, it's Z to the 1 with probability P1, etc. Okay, so with these 4 properties, we can actually sketch this probability generating function on a graph with Z as the horizontal axis and Y as a vertical axis. And it's convenient to draw in the line Y equals Z. And what I'm going to show you is true is that little intersection that I've circled gives us for a probability that the process will go extinct. Now, if you look at this, the gradient of the curve at 1, this is a point 1, 1, where recall from the properties of a PGF, when we put Z equals 1, we've got the sum of probabilities, so it's 1. The gradient at 1 is the expected number of cases. So if that gradient is 2.5, it says if we had many branching processes going on, the next generation would have 2.5 times as many, the next generation 2.5 times that, and so on. So the epidemic would take off on average. Once it's taken off, that would be true, but there's always a possibility of the epidemic going extinct, and I'm telling you that that's given by this value here, the height, the Y coordinate of that value, and I'm going to show you why. So we move down.
there's just a question.
Yes, yes,
So Ian McCulloch is asking, is the slope at z equals 1 the same as r0?
yes, yes. That's correct. It's the expected value of the R0 is the expected number of offspring of the cases. I'm assuming that this is when there's no interventions. And what I'm thinking of is that after we've had a campaign of elimination, we take the brakes off entirely. It's obviously a caricature of what we do, but we take the brakes off entirely and we go back to that slope of R0 equals 2.5. Now, if you're mathematicians, you could say, well, what about if the slope's exactly 1? That's not of interest if we're epidemiologists dealing with whether the epidemic's going to take off or not. But it was of interest in the 19th century to people discussing the inheritance of British surnames. It's of interest in modelling antigenic drift. But we're just going to deal really with the case where the epidemic, if there are large numbers, it would be taking off. Okay, so the first step in getting to the point of a proof, that intersection I pointed out on the graph, gives us the probability of extinction. The first step is to consider outcomes when we've got two branching processes. Now, I've got a rather difficult sentence here, but I'll make it concrete. Let's say we were dealing with two identical independent branching processes where there could only be 0, 1 or 2 offspring with probability P0, P1 and P2, and we are summing the total number of offspring of those two processes. And let's say we are wondering, what if the total, what's the probability that the total is say 2? Well, if, the way we could get that is that we could think that the first process gives no offspring, the second process gives 2, or both processes give 1, or the first process gives 2 and the second process gives 0. Also, if we multiply out this probability generating function by itself and look at the coefficient of z squared, we get exactly the same term. Now, that's just an illustration of what you can show more generally, and that is multiplying probability generating functions give coefficients which correspond to the probability of the outcome for that power of z. In other words, the probability generating function of x1 plus x2 is just the probability generating function of either of them raised to the power 2. So in the expected value notation, it can look which is expected value of z to the power x1 plus x2. It's the expected value of z to the x1 times the expected value of z to the x2. So it's this expression. Okay. Now we can extend what we've just done with the sum of 2 branching processes to the sum of k branching processes, and we get we just get the its probability generating function of that sum of branching processes, just a probability generating process of 1 raised to the power k. So now we're going to take it a little bit further. Instead of having k, a particular number, we're going to have that value k as n, a random variable itself. And to be concrete, we'll say that n takes the values 0, 1, 2 and 3 with these probabilities. And so n has this probability generating function. And so we want to find the probability generating function of the sum of all the x's up to the nth x, whatever n is. And we do this by conditioning. And if n equals 0, and that happens with probability g0, our term is e to the expected value of z to the 0, that's 1. If n's 1, we've just got one probability generating function. If n's 2, we've got the sum of two probability generating functions. So we've got a probability generating function squared. If n's 3, we've got the probability of generating function cubed, and so on. And we can sum over all the possibilities for n, and we get this expression. And if we look back at the probability generating function of n itself, what we have up here is just exactly the same as down here, except the z is replaced by phi of z. So our general result here is that a probability generating function of this n random number of random variables is phi n of phi x, phi subscript x of z. And now we take n to be the number of offspring of the primary case in a branching process epidemic. x1, x2 up to xn are the offspring of the secondary cases. So the number of tertiary cases is the x1 plus x2 up to plus xn. And the n, it's got the same probability generating functions as all of these. They're all the probability generating function of a case giving rise to a certain number of offspring. So we have a result that after 2 generations, a number of offspring is given by phi subscript x of phi subscript x of z, and we'll denote that with phi subscript x raised to the power with brackets 2 of z. And with 3 generations, we get with a little brackets 3 and so on. Now, what we're interested in is extinction. So we're interested in the case, the instance where we go many generations, k generations down, and extinction, if we remember our probability generating function definition, we get the epidemic. There's no cases then, with a probability we get by substituting naught into the probability generating function. Is that okay? So that's when k is large. And the other thing we should note is that this sequence is increasing. So that's the probability of having no offspring just in the no secondary cases. It's the probability of having no tertiary off cases and so on. Well, it has to be getting more, because you could have first generation offspring, but they all the second ones go extinct, or all the third ones go extinct. But so this is an increasing sequence, but it's got an upper limit. Their probabilities, they're limited by 1, so we have a limit. So so we'll put u as the limit, and we have to remember that the way we go from the k to the k plus 1 is we just take phi subscript x of the what's in the previous, of the probability generation for the previous number of cases. So in the limit, we have this equation, u equals phi subscript x of u, that gives you the probability of extinction. I think that's a beautiful result. And so there is, if we think back to our earlier curve, if I can get it. Where is it? Where we, it's not worth finding. Here it is. There's two intersections in the if we're looking for a solution to u equals phi subscript x of u, there's two intersections of a curve because it's a convex curve. Here's a straight line. There's a little graphical proof that I won't go into, that we should always go for the lowest solution. Now I'll swap over my share so that I go to my paper. Just bear with me a moment. Okay, so now I'll discuss my actual paper, and what I'm considering, as I said, is that we know we can have elimination. China, or at least presumptively, has proven it. New Zealand's going for it. So I think we almost know that. I'm assuming that we're going for that process of elimination quite early on, and we're going to suddenly take the brakes off, and it's open slather. R naught's going to go back to 2.5 because we haven't got herd immunity, if indeed that ever occurs. But we're assuming that we're going to keep our borders closed. Now, there's a worry because of asymptomatic cases. I'm not in a position to have any good ideas on how many asymptomatic cases there are. There's a lot of cross-sectional studies which seem to suggest that it could be about 1 for 1 asymptomatic case for each symptomatic case. There's now the antibody testing. I'm not sure how reliable that is. I think it's probably less than 50%. I'll be generous to the people that worry about asymptomatic cases and take it with 50%, but maybe I'm wrong in saying that's being generous. In any case, if I've taken it as 50% and somewhere in my programs I've scrambled up this, I'll call it probability of asymptomatic P subscript A is 50%. If I've scrambled up PA and 1 minus PA, it won't make a difference, but I hope I haven't done that. All right, so we'll go down to methods, and perhaps I should say why I actually thought of doing this. And what occurred to me is that the Chinese government, I think it was the 23rd of January, decided that Wuhan was so dangerous that nobody should leave it. But it took I think, but actually at the time, at the hour they decided it, a plane had just taken off from Wuhan to Australia. And then we got a number of cases in Australia. I suspect, I don't know, that a lot of those cases were on that plane, or possibly they were on subsequent planes from China, because we didn't close travel from China for a week or two later, and we didn't close travel from other countries, which obviously had an epidemic to some time after that. But it was quite some time after that first flight from Wuhan that we started getting community transmission. So what occurred to me is that it might actually be a bit uncommon to start off a branching process. So I played around and I thought of this scenario where perhaps 99% of people who are infected spread it to no one, and 1% of the people spread it to 250, and that would give us our R naught of 2.5. But clearly, since if we choose an infected person at random to come and cough and wander around Australia coughing and sneezing, but doing it in a way which because they're not a super spreader, it doesn't get to anybody, there's over 99% chance that that the community transmission in Australia won't take off. And even if they are a super spreader and they spread it to 250 people, well, maybe none of those 250 people they spread it to are super spreaders. So basically, we have to solve this branching process equation of phi u equals u. And for this particular very contrived probability distribution, where 99% spread it to no one, 1% spread it to 250, it works out there's a 99.1% chance that a single introduction into Australia wouldn't spread it. So then I tried other quite contrived distributions that were less and less skewed and less spread out than this one. And then I thought, well, I should try some real distributions. And I tried two standard probability distribution, the Poisson and the negative binomial. And it was interesting that there's actually been, somebody's been able to get a little bit of a handle on not just R naught, but on the distribution of the number of offspring whose expected value is R naught. And I don't know how reliable their paper is, but they've got an estimate which gives a very, very skewed negative binomial with a large weight at 0 and a very long right tail. Not that far different from this one, really. They did that by looking at how in various comparable countries in the earliest phase of the epidemic, when presumably they were looking at just the primary case and the primary plus the secondary cases, how big they were before the epidemic took off. Somehow or other, they got some indirect information on this. So now we've got to add in the fact that there are what we're doing, and what we're doing is we're down to a single symptomatic case. By the time we find them, they might have already spread the disease. And I assume that anybody they've spread it to, well, it's going to take off with if it hasn't gone extinct, R naught equals 2.5 will apply from the time we find this symptomatic case. And but the symptomatic case is then isolated, but maybe there are these asymptomatic cases. And how many are there? Well, on average, I'd say there's one, but we don't know how many. It's obviously going to be a random variable. And as a Bayesian uninformative prior, I'm taking the distribution to be geometric. And I'll just stop sharing this and go back to the previous document, because I've got a little proof that shows that if this was to apply, that if there was a descendant from the symptomatic case and then descendants from asymptomatic cases, and we lifted our foot off the brakes at time 0, when we were just down to our last symptomatic case, then the probability that there'd be total extinction is given by this equation. So I'll stop sharing this one, go back to the previous one, and if I can find it, yes. And I've got a little derivation here. So we're saying that the asymptomatic are going to follow this distribution. K can be 0, 1 or 2, it's geometric distribution. And we'll assume a symptomatic has spread it. And maybe there's no symptomatics, and that occurs with probability 1 minus PA. The symptomatics are isolated, but their line, since we assume they've actually spread it, which is a generous assumption, will go extinct with probability PE. And so in this case, overall, the probability is 1 minus PA, PE in the case K equals 0. In the case K equals 1, then there's 2 lines that have to go extinct. This situation where there's one symptomatic and one asymptomatic occurs with this probability. So we have this expression for the probability given that there's one asymptomatic of the processes extending from this going extinct, is that. Similarly with 3 asymptomatics and so on. So we've got this sum and that gives this expression. So P subscript T0 is an analytic calculation. I'll stop sharing this and go back to the paper. Sorry, let me, I think I got the wrong one there. Can you see that?
Yeah, we see it, the paper. Mm-hmm.
Yeah. All right. So I can get an analytic calculation for probability of extinction, assuming we've got our last symptomatic. We've actually spread it to one person, but then there's prior to being isolated, but where there's also perhaps 0, 1, 2, 3 or so asymptomatic cases, and they're also spreading it. But given that we're dealing with a stochastic process, there's still a probability of extinction that's given by this. And so these are all the distributions I consider, but I give you the results and I just put in a little column of the coefficient of variation just to show the more variable the distribution is, the more easy it is to get extinction. And we've got here ability that everything goes extinct just from a single case, and here's the probability that the lines go extinct, even though we've taken a foot off the brake. On average, there's an R0 of 2.5, but because there's a lot of that 2.5 might depend on super spreaders who are quite uncommon, there's still a fair chance the process goes extinct. This case 5 where it's 0, that's the case as near to deterministic as possible, whereas we're assuming that the symptomatic case has already spread it to one person and now spread it to either 2 or 3 people, and there's no chance of not spreading it to anybody. Now, cases 7 and 8 of a more interesting one. This is assuming that how the distribution that's behind that expected value called R0 is a Poisson distribution. That's a distribution where there's total randomness. It's like a lightning strike in a particular square kilometre in a year. It can happen 0 times, 1 times, 2 times, whatever. And no person has a particular proclivity to be a super spreader. It's pure happenstance. And that gives quite a low probability of extinction, because if on average people spread it to 2.5, it's quite uncommon relatively that they spread it to no one and the process goes extinct, and even more uncommon after a few generations. Add in asymptomatics, and if you take your foot off your brake and it goes back to an R0 of 2.5, as soon as you got to the last person, then the epidemic has only got a 5 or 6% chance of not re-emerging. Whereas if we've got this negative binomial distribution, for which there is a little bit of evidence, well, even if we take the foot off the brake, as soon as we get the last, we're down to one symptomatic case, there's still a better than 75% chance that there won't be any, the epidemic really will go extinct. Any remaining cases are unlikely to include a super spreader, or even if they do, that's pretty unusual and they won't be spreading it to super spreaders. Now,
just to make sure, a question, David. So all these distributions you took, 1 through 8, all of them have a mean of 2.5. Right?
That's correct.
So
these are, I scrolled through this too quickly, but yes, they all have a mean of 2.5. So an expected value of 2.5.
So you're showing that when we're down to the last few cases, it's really the shape of the distribution that determines the behavior. And
that's correct, exactly.
Okay. And what's the difference again between the column PC and P subscript T0?
That's PE, sorry, it's very small. PE is the probability of a single line going extinct. P subscript T0 says what's the probability if there are, in addition to the single line, there's asymptomatic cases we don't know about, on average 1, but geometrically distributed.
Oh, I see. And one more thing, why did you call it uninformative prior if the asymptomatics are geometric? What makes sense?
Yes, well here I'm a bit rusty, I have to admit. So
is it like the case of
Bayesian
knowing
statistics,
nothing, in a sense?
people try and find ways of saying, well, if you don't know anything about a discrete distribution, but its mean value is 1, and we've got to use that as a starting point, what distribution should we choose? Which distribution doesn't suggest any prior knowledge? And really I can't, without brushing up on my Bayesian stuff, which is very rusty, I can't say any more, but I'm sure there are people here that will be able to correct me or whatever.
That's good. Thanks.
Okay.
Oh, Paul Bellett, just letting you know, there's a comment from Paul Bellett that it's a maximum entropy distribution for fixed moments.
Okay.
I didn't know that. Thanks, Paul.
Thank you very much. Look, I'll have to look it up. I just remembered the concept very vaguely and stuck it in without checking enough on. Yes. Anyhow, I thought we should go into more detail with the 2 distributions which are less contrived, the Poisson and the binomial, for which there's some evidence. And with the Poisson, there's only one Poisson we can choose because the mean fixes the Poisson. So if they've taken the foot off the brake and the Poisson's got a mean of 2.5, that's the only Poisson which has a mean of 2.5. And what I've done there, I tried to go further analytically, but it was too hard, and perhaps better people could get some very involved analytic expression for along the lines of a much more involved expression in like U equals phi of U, but I did the rest by simulation. And the P subscript T1 says it's a branching process in discrete time. Let's say we wait an incubation period. And if during that incubation period a further symptomatic case arises, or at the end of that incubation period, since we're in discrete times, there's another symptomatic case, we go back to the beginning and wait another incubation period. If there's no, and so on. But once there's no asymptomatic case after an incubation period from there being one symptomatic case, we take our foot off the brake. What's the probability of the epidemic re-emerging? And by stimulation, in the case of the Poisson, it's about 61%. And in the case of the negative binomial, it's 98%. Whereas if we took the foot off the brake, we've already calculated these analytically, it was only 6% if we took our foot off the brake immediately, and about 75% if we took our foot off the brake immediately, Poisson versus negative binomial. But we bring those percentages right up if we wait an incubation period. If we wait 2 incubation periods, we can see if the negative binomial distribution is true, we're virtually guaranteed to totally have eliminated the epidemic. Well, if you want to gamble the country's future on a 99.87% probability, but in reality, we won't suddenly take our foot completely off the brake and tell people to go to as many sporting matches and love-ins as possible.
Can I ask another question?
Yes.
So just to understand that you had a random variable n, which is the number of people that are infected when you take the foot off the brake. Is that correct, or is that a single infected when you take the foot off the brake?
A single infection that's symptomatic, but an unknown number, but geometrically distributed around one of asymptomatics.
So right, but a single, I mean,
one asymptomatic for each symptomatic.
Right, but I mean, well, I assume if when we take the foot off the brake, you know, there'll be kind of a handful, you know, some random number which is around 20, 30, 40. Do you not believe that, or?
No, well, what I'm saying, and I'll come to that in the discussion, is that a strategy will be not to take our foot off the brake until there's one, but that might be difficult, but you can do it sub-region by sub-region. So in North Queensland, I think we've got none at the moment. No symptomatic cases except the ones which are totally isolated. So we could take the foot off the brake here right now, and these probabilities would apply because we're now down to none. In South Australia and Western Australia, I think that's true as well. But in Brisbane, I don't think it's true. In New South Wales, it's not true. But we could do it sub-region by sub-region, and provided those sub-regions, at least for an interim period, are isolated from travel between each other, we could have a strict rule of taking the foot off the brake when there's just one, or even one incubation period after there's one and no more emerge, or 2 incubation periods after we've got down to one and none emerge. I think this is what New Zealand's doing. We can do it in Australia, but there'd be impatience. But if we did it sub-region by sub-region, we could probably do it.
Gotcha. Thanks.
Okay, so so a discussion. So why am I pushing for elimination? Elimination requires more intense lockdown than the policy of flattening the curve. So that's a bit of a hardship. Flattening the curve says let the epidemic go, but don't let it rip. Just let it go slowly, so it's within the capacity of the region's ICU bed, the country's ICU bed numbers. So that's been, I think, explicitly Australia's policy, and we've gone for flattening the curve. But thank God we've overdone it. Now, there's a study by the Imperial College, which I've referenced, and it shows there's two rather fine lines with the flattening the curve policy. So the idea of flattening the curve is we stay within the country's ICU bed capacity by having a smaller and delayed epidemic, but then we have enough cases infected so we get herd immunity. Now, herd immunity is becoming a mirage. It seems like people can get the disease again. The immunity might not be long lasting at all. And to flatten the curve sufficiently so we got herd immunity, we've got to have lockdown measures which are pretty severe, almost as to have sufficient flattening of the curve. We might have to get the R0 down from 2.5 to 1.2. That's quite severe lockdown, but the problem is it has to last for a year or so because the epidemic curve is delayed, and it's delayed for what will likely be a mirage of herd immunity. In fact, if we flatten it sufficiently, it might still take off slowly over a year or two and peak and come down again without there even being sufficient immunity for herd immunity. Even if there was real immunity, there might not be enough people infected for herd immunity if we try and keep within the capacity ICU. The other thing is people still die in quite substantial numbers if we have an epidemic, even if we've got ICU beds. So there's a fine line between an insufficiently flattened epidemic and having a herd death rate and a sufficiently flattened epidemic. But if we get it down below 1.2, in Australia we've probably erred and gone down to 0.8. So we're not, even if the ambition was some, I think, misguided aim to get herd immunity, we can't get it because we're actually suppress the epidemic. So I think we should go for elimination. So the problem with elimination is that things are not going to go back to normal entirely. We won't be able to have international travel without quarantine between countries that in the future will be certified COVID-free, and countries which aren't. That won't be possible without quarantine if our aim is elimination. But in any case, I think international travel is in the future will be problematic. I think our world has changed. I think it needed to change. We've got lots of other problems with climate change, etc. We need to change. My fear is we're not going to change enough. But anyhow, I think if we did have elimination in Australia, we could get back to normal. It would be good socially for us in Australia as well as economically. Okay, so there's a lot of limitations of this study. So I haven't done any sensitivity analysis sort of what about sensitivity analysis on the PA probability of the proportion that are asymptomatic. It's based on a branching process in discrete time. There's a direct analogy to a branching process in continuous time, but unfortunately it's a very contrived process in continuous time. It assumes that anybody gets infected has an infectious period from that time that's exponentially distributed, and all their cases are generated at the end, and then they become non-infectious. Ideally, if we were going to do it in continuous time, we'd need to model something in a more sophisticated way, and it'd have to be done numerically by simulation. But I don't think it'd change the principles that are yielded. It needs to be checked. Now, there's some assumptions that are too pessimistic here. For example, we're controlling it also not just by lockdown measures, but by contact tracing. On the other hand, I might be being too optimistic. So there could be long-term carriers of the virus, and or it could even be animal carriers, but we haven't got pangolins and Chinese bats in the region, so hopefully there isn't. And so I think this gives us cause for optimism that we will be able to eliminate this disease, but without, and the prolonged moderate, rather intense lockdown actually doesn't have to go as long to achieve that end as people may think. And let me just conclude as a GP who's got no knowledge of particular good knowledge of infectious disease, but I can see in a world where countries have COVID, that when you're a newborn, you might get COVID and get very sick. You might survive. When you're a child from it, you'll get a few colds every few years or so. When you're an adult, you'll probably be all right for a while, but if you get pregnant, or if you get cancer or an autoimmune disease and need immunosuppressive therapy, you might get pneumonia and die. When you get old, every year it'll be endemic and you'll have a chance of getting it, and it'll knock a substantial number of years off the life expectancy of any country which chooses to or doesn't have the resources to eliminate COVID. That's my worst case scenario. That assumes that we're not going to be clever about treatments and vaccines, but I think we might be being too optimistic about those things. Anyhow, that's all I've got to say. I'm happy for questions.
David, that was great. Before questions, let's the typical we do this 3, 2, 1 clap. So 3, 2, 1. Thank you. Yeah, so thanks. I'm not sure that some people were not 3 weeks ago when Zoltan spoke about the deterministic SIR, and now you presented the kind of the stochastic system that somewhat couples that, at least with the first few cases. So yeah, questions. So I'll start with one. So I found your presentation interesting, and it was nice. I mean, that key table seemed to have somewhere around page 5, maybe. It had, I think, a key message, if I understood correctly. So you're saying there could be different distributions of spreaders, and they're really about the characteristic of the spreader. Is that correct? If she is a super spreader or
yeah, I'm saying that most of that R0 might be down to quite a small proportion who are, you could label them super spreaders. Of course, there's a distribution over all the numbers of secondary cases, but it could be that most of that are not. In fact, in a lot of things, like in nodes in social networks on the internet, or in sexually transmitted diseases, some people are much more likely to be spreaders than others. There's quite a skewed distribution. Yes.
Right. So is there, I mean, making inference of which of these cases 1 through 8 we're in is probably difficult to know.
Yeah, well, there's evidence for 8. I mean, 1 to 6 are very contrived distributions. They're just made up to satisfy R0 equals 2.5, just to show that within R0 equals 2.5, you get quite different consequences at the end of the epidemic, and indeed at the beginning of the epidemic. But options 7 and 8, Poisson and negative binomial, could be more or less real. And I think the negative binomial is much more likely than the Poisson, because I think people's activities are generally negative binomially distributed rather than totally random, like lightning strikes, as is assumed by the Poisson. And the negative binomial gives us a much more optimistic message for the elimination of the epidemic if we continue on our current course.
Thanks. There's a question written, you might not see the chat, from Michael Small, and he writes, can you look for comparison at a power law distribution?
Yeah, that's a very good question, because in apparently in theory of networks, the power law is what seems to have some practical and theoretical underpinnings. The reason I'm using the negative binomial is simply because the paper, it's an unpublished paper for which there's a preprint, but so I've referenced it. It's an unrefereed paper, but they came up with that negative binomial based on some data, and that's the only one. That's all I could find. But I doubt if it makes that much difference. The power law might be even better, but I didn't try, I wasn't fitting any data, and perhaps I should have put the power law down there. But I mean, there's, what would I have used? There's more than one parameter, so at least with a Poisson, there's just one parameter. It's fixed by the R0. With the negative binomial, there's 2 parameters, and one was fixed by at least very preliminary information.
Yeah. Hi there, sorry, it's Michael here. Sorry, I've got my kids screaming in the background, so I was typing rather than talking. So I guess some of your distributions 1 through 6 are kind of like an approximation to a power law, right? You have a small probability of a large number of secondary cases and a high probability of very few cases. Is that?
Yes. Yeah, well, I suppose that's true. Look, I've got to confess that I'm a bit rusty. I didn't even think of a power law until after I was looking for references for this paper. But yeah, if it's a distribution with a long right tail, it is optimistic for elimination. And that's probably true. However, whatever distribution with a long right tail in which we try and fit whatever data we can get.
Yeah. Okay, thanks.
Are there any other thoughts, questions, even questions about the basic branching process from the start? I'm sure not everybody's seen this before. Anything else?
I was kind of wondering, so Yoni, I think you sent that email around earlier with the Safe Blues program, right?
Yeah.
So with the, so this is, I guess, back to David. With working out the distribution, one thought that I had was that if you were able to simulate these if you were able to simulate and see how people are actually interacting given some process rather than just a contact tracing with some sort of essentially modeling, getting people to model people using this Bluetooth programs to work out what the distributions would be. I guess that's one thought that comes to mind. If you could do something like that, then maybe, I guess you could use that to work out the distribution and see whether or not you should put big lockdown, how you should proceed, essentially.
That sounds like an excellent suggestion. Right. Yeah. That's a very, very good idea. But one tiny reservation I had about the Safe Blues thing, I think it's an amazingly good idea, but there's also this, and I think we should be wearing masks, because I think a lot of the transmission is by droplets or through cruise line air conditioning units, hopefully not by shopping centre air conditioning units, but most of it's by droplets. But what we're being told is because there was a shortage of masks and they were too embarrassed to say that's why we're not recommending masks, they told us to wash our hands. But that is relevant because some of the transmission is not by just coming close to each other, it's from what they call in epidemiology fomites, from handling commodities which have been handled, or surfaces which have been handled by other people. So the Safe Blues won't quite incorporate transmission by fomites necessarily, which does seem to be
I was wondering whether it might actually be.
But I think Yanni's Safe Blues and your suggestion are absolutely excellent.
I guess one question might be also, would you expect how different would you expect distributions given different spreading behaviours? So this might be used for COVID, but could you use these kind of procedures in the future for just like the standard flu or anything else, where the spread might be, it might be that it's more infectious or less infectious, or it's going to become quite obvious, so you're going to know when you're infected, and so on and so forth.
Yeah, well, I'm sure all our modelling approaches for COVID are relevant to other respiratory-borne infections. Yeah, but this one's important. This one's more important than the flu, because it's going to the flu might only affect a rather small proportion of the population, because there's no immunity to the population. It's going to infect most of us if we let it rip. And there's also funny things cropping up, like young people with minimal respiratory symptoms are having strokes as a result of this. So it's more important for modelling for this than for the flu. This is a much more serious condition than the flu, in my opinion, anyhow.
Yeah, I guess I was thinking long term, and if we don't know precisely how this really spreads, we could run several models,
yeah, of course,
in theory, at the same time.
Yeah.
And work out which one seems to fit the results best, along with working out whether we have high or low social distancing.
Yes, that's a good suggestion.
Yeah, I think we should close just because it's 9:05, and yeah, this was very good, David. And David. Was this just a set? So you listened for the first time last week, right?
Yes.
Yeah, and you immediately took up the job of presenting, and we really appreciate it. So thanks again. And
well, thank you very much for inviting me.
Yeah, Okay, great. So there'll be announcements about the following talks, and if anybody else wants to give a talk, you've seen there's Cecilia presented last week non-original research, or you can present original research, or a collection of experiments and views, which is also great. Just go for it. So have a good night, everybody. Thank you.
Thank you.
Thanks.